Okay, welcome back. So if you recall what we did in our last class, we were talking about series solution about a regular singular point or about regular singular points, right? So what we did, we were still into a second order linear differential equation given in this form, right? And then I told you that, x equal to x naught, it is called a regular singular point of this given differential equation if xpx, and sorry, not xpx, if x minus x naught px and x minus x naught whole square qx, they can be expressed as power series, of course, convergent power series about the point x equal to x naught. Okay, so basically, if these two expressions, say small px equal to this and small qx equal to this, they are analytic about the point x equal to x naught, we say that x naught is a regular singular point for this given differential equation, right? Okay. So now again, I told you that I am seeking a series solution of this equation A about the point x equal to x naught, and then I also told you that when we were considering your Lysender's equation. So over there, what we did, we tried to avoid these singular points, and rather what we did, we found solutions about a point which was an ordinary point, not a singular point. So now we'll try to find out series solution about your regular singular points. Okay, fine. So now, if I fine. So probably you already know, you have definitely done this before in your BSc and MSc, and you have seen that if I take a solution, of this form, say n equal to 0 to infinity, a n x to the power n, if I plug this in here, it seems to work. I'm not saying that it definitely works, but it seems to work, right? Is it okay with everybody? Yes?
Yes, sir.
Yes. Okay. So can anybody tell me that what is this type of series solution called, or what is the method called? If you plug in solutions like this in the given differential equation, there is a name for that. Can you recall that?
Frobenius method.
Frobenius. It is Frobenius method, or this kind of series, they are called Frobenius series. Okay. So did you ever thought, did you ever think, why this approach works? Why this approach works while trying to find out, series solutions about regular singular points? Did you figure it out, or you just simply plug that in the given differential equation A and then found out the solution? Does anybody have any idea why it works? Okay, fine. It seems that although, maybe you have studied that, but still, the concepts were probably not very clear. So I'll try to explain that. Where did this idea of Frobenius series come from? Okay, fine. See, suppose I consider a differential equation. For which x equal to 0 is a regular singular point. Even if x is not equal to 0, you already know that through some shifting or by some transformation. So basically, if I plug in, p equal to x minus x naught through this transformation, I can easily convert this differential equation into an equation where y is going to be a function of t, and we are going to seek solution about t equal to 0. In that it is going to work, right? So what I'm going to do, I'm going to take the simplest equation, simplest differential equation of second order, right? Where x equal to 0 is a regular singular point, and probably you are aware of solution of equations of those type. Okay, so obviously, if I consider something like this, say where my t is a constant, right, and then q by x squared y, this is equal to 0. So obviously, this equation, for this equation, you know that for the known reasons, x equal to 0 is a regular singular point. Is it okay with everybody? Is it okay with everybody?
Yes, sir.
Yes, sir.
Yes. So now, as you know that this could, this could have been put in this form. Ps y prime plus q y equal to 0. So obviously you know that. So this is in Cauchy Euler form. Cauchy Euler form, and you can easily solve it. Is it okay with everybody? Right? You can easily solve it. Okay. And you know that what we did, this could be solved by, grouping in the optical equation approach, and then this was like what Pm plus Q equal to 0, right? Okay. Firstly, what we did, and you know, where this idea comes from, you already know. If you plug in x equal to something like log j or something like that, and from there, this is going to come out. Is it okay? Fine.
Yes, sir.
J equal to e to the power x. Okay. So then this is going to come out. Okay. Fine. Anyway, so then once I solve this equation, so obviously this equation is going to give me, say, two roots, and for the time being, let us assume that these two roots are real. Of course, even when it is complex, it is going to work. But let us stick to, for the time being, because we are going to consider, series solution. For the time being, let us assume that they are real. Okay. So then you know that if your m1 is not equal to m2, then your solution is going to be of this form. Y is equal to something like c1 x to the power m1 plus c2 x to the power m2, right? And if your m1 equal to m2, then what happens? You have solution by x to the power m1 plus c2 x to the power m1 ln x. So this happens when your m1 equal to m2, right? You have already come across this. Is it okay with everybody? Fine? Isn't it? Right? So basically, if m1 is not equal to m2, I can easily find out two linearly independent solutions of the form x to the power m1 and x to the power m2. Otherwise, if m equal to m2, then I have what I do. I just simply, plug in ln x here, and this comes from linear equation of constant coefficients concept. Where in the auxiliary equation you have you have two equal roots. Okay, and ln x was simply that substitution, j equal to ln x. From there, this term comes out. Okay, fine. So now let us see what is happening here. So, okay. So this was my form. Let me retain this too. Okay, fine. We can erase these also. Okay, fine. So what we have learned so far, that if I have an equation of this form, then my solutions are of this form. I mean x to the power m1. I mean pair of solutions, x to the power m2 or x to the power m1 and x to the power m1 elements. Fine, so far so good. So now see this one was a differential equation which has regular singular point, but in the original equation, if you look at the original equation, these terms were constants, okay, which is not likely to happen in each and every case. Is it okay? Fine. So the most general form of a second order differential equation having regular singular point x equal to 0, I can definitely write it as something like this. So instead of p being a constant, now p is a function of x. Similarly, q is a function of x. Fine. Q is a function of x, and this is equal to 0. Is it okay? Is it okay? Fine.
Yes, sir.
Yes.
And if I assume that p, this small px and small qx, if I assume that this small px and small qx, they are analytic about the origin. They are analytic about x equal to 0. So then definitely I could have written this as something like p0 plus p1x y prime plus your 1 by x squared, your p0 p1x, something like that. This into y, this is equal to 0. This is equal to 0. Is it okay? Fine. Fine, so far so good, right? So this gives us an idea. Now what you have to do, you simply compare this equation and this equation. You simply compare this equation and this equation. The only difference is that here I had constants p and q. Now those p and q, they are replaced with infinite series like this. They are replaced with infinite series like this. Is it okay for determining? Is it okay with everybody? Right? The only difference is that these constants p and q, they have been replaced by some infinite series. Is it okay? So that gives an idea. That if with constant coefficients, the solution of this equation is of this form, right? So then probably, I'm not saying that definitely it is going to work. Then probably the solution of this equation is going to be of the form x to the power, say, m1, x to the power m1 into, because say this one I could have written something like what? This one I could have written something like, say, p0 into 1 plus p1x and so on, right? And then this p0 is equivalent to this p, right? I still have an infinite series multiplied with that. So that is why probably multiplying the solutions of this given equation with an infinite series, which is a power series, is going to give me a solution of the most general form of the second order linear differential equation having regular singular points at x equal to 0, and I am going to find a solution of that form. Probably that solution of this form is probably going to work. Yeah, fine. So that is where the idea of Frobenius series comes from. Is it clear now? What is the rationale behind choosing a series solution of an equation of this form having regular singular point at x equal to 0 in this form. Is it okay? Fine?
Yes, sir. Yes.
See, you may be thinking, I mean, why some of the things are being repeated here? Obviously, I'm absolutely sure that some of the stuffs, I mean, you didn't learn earlier. Like say, probably your syllabus was different, and even say my syllabus here for this particular course doesn't tell me to explicitly teach you something like this. But you know, in all your PhD courses, you this, I mean, probably by now you would have realized that I mean, we are emphasizing more on the concepts. You may be wondering why. See, we have some selfish agenda here also. One thing is that you guys are going to work as our teaching assistants from your second year onwards. Okay, once you I mean clear your comprehensive exam, after that you guys are going to work as TAs, right? So then basically you are like some mini professors, right? So you have to teach the students. So then you will come across all type of questions. They are going to ask you different questions. So we need to prepare you for those situations. So, and not only that, you should know concepts, right? Your concepts should be clear. It is another thing. But we also have some selfish agenda behind teaching you all this stuff like this. Okay, fine. So now the and another thing. Let me come back to Frobenius series once again and let me tell you one thing about it. Okay. Okay. So now I have told you that for this equation, we are going to seek solution. We are going to seek solution of this form, you know, 0 to infinity, or if I expand it, it is going to be something like this. Here, one thing you have to remember that we are always going to assume that A naught not equal to 0. A naught not equal to 0. And why that is so, probably it is obvious to you, is that if A not equal to 0, again, see, this could have been, in case say, if A not equal to 0, this could have been, you don't have to write it down, like say, I could have done it like what? A1 plus A2x and so on, right? Since I'm already writing this as an exponent of x, so it makes sense that whenever you assume that your series is something like x to the power p, like c and x to the power n, you assume that your at least c naught not equal to 0. Is it okay? Because eventually you can easily absorb it. So that is why from the very beginning, I'm simply going to assume that A naught is not equal to 0 here in this particular. Is it okay? And you will see that this is very, very important. This statement is very, very important. Okay. So now let us see whether this approach works or not. Okay. And after a while, I'm going to tell you why this approach works. Although we already have an idea that why it works, because it has some relation with some constant coefficient cases, right? So that has shown us a path to, move ahead like this. Okay, fine. So let us take a very simple equation. Okay, fine. Suppose we are trying to solve this equation. Okay. And again, I'm going to simply straightforwardly substitute the expressions. Okay. So obviously, you can see that x equal to 0 is a regular singular point, right? Okay. Fine. So I am going to, I'll try to find a solution about x equal to 0 here. Okay. Just a minute. Yeah. So now, see, I am assuming that the solution is of this form. Okay, fine. So now, once I substitute it here, so what it is going to be, I'm going to erase it. So I'm just going to ask you a silly question. So this will be substituted with what? Because that becomes x to the power m plus n. So n plus n minus 1, then x to the power n plus n minus 2, right? And n goes from 2 to infinity, right? Yes?
No, sir. 0 to infinity.
0 to infinity. 0 to infinity. Okay, so don't do this mistake. Because earlier, when we were considering, a solution about ordinary point, we didn't have this term multiplied. Okay, so now, because this term is multiplied, so it is not going to start from, because what is going to happen? Your series is basically what? A naught x to the power m, a1 x to the power m plus 1 plus a2 x to the power m plus 2, and so on. Isn't it? Right? So now if you differentiate it twice and then again you want to retain the series, so this n is always going to start from 0. Remember that. Don't do that mistake. So now, because we already know that, so what I'm going to do, I'm going to directly substitute all this stuff. So now if you multiply it by x squared, if you multiply it by x squared, definitely this minus 2 is going to go away. Okay. So then again here, what I'm going to get, n equal to, I missed one term, this an. Okay. So an as before, n plus n, x to the power n plus n minus 1, but I had it multiplied by x. So again, this is going to be x to the power n plus n. And again, I just want to do one thing. 0 to infinity, an x to the power n plus n. Because of this x, this is 1. Okay. And again, 0 to infinity, an x to the power n plus n. So this is equal to 0. Okay, fine. So again, what you have to see, the very first power of x in each of those series. So now here you can see that. These start with x to the power m. These again start with x to the power m. But these start with x to the power n plus 1. Again, these start with x to the power m. Right? So then what we'll have to do, the very first term of the remaining series, we have to take it out. Is it okay with everybody? Just we did it in our ordinary, series solution about ordinary point. Okay? Fine. So then what I'm going to do, from each of this one, and this one, I am going to take the first term out. So then this is going to give me 2 a naught, because n equal to 0. So then I am going to have m into m minus 1. So first term I have done for this. And then for this one, the first term is going to be a naught and simply m. And from here, first term is simply minus a naught. Fine. So then what is going to happen? This series is going to start from n equal to 1. So if it is start from n equal to 1 to infinity, so then then what is going to happen? Like this one is n plus n plus n minus 1, then an, okay, that's like that. And then for this one, again, it is going to start with n equal to 1. So I am going to have n plus n an. And see, now maybe I'll write this one down and then I'll come back to this. So this also, because I have already absorbed the term corresponding to n equal to 0. So again, this also start from n equal to 1. And then I am simply going to have minus an. Okay. So now let me come to this one. So now you can see that this one is starting from n equal to 0, but the very first power it was actually for n plus 1. So if I plug in simply your n plus 1 equal to p, n plus 1 equal to p, so then what is going to happen? Corresponding to n equal to 0, your p is going to be equal to 1. So again, this is going to start from n equal to 1. But once n plus 1 becomes equal to p, so then n equal to p minus 1. So basically what I am going to do, I am simply going to replace an with, well, a n minus 1. Is it okay? Fine. A n minus 1. And of course, this is here. I am going to give x to the power n plus n. So this is equal to 0. Okay. So now what you have to do, you have to equate different powers of the coefficient of different powers of x to 0. Okay. Fine. Okay, so that brings us here. See, this is a naught 2 n to n minus 1 plus n minus 1, right? So this is equal to 0. And from here, see, again, this I could have written as this, right? So I have like I have n plus n minus 1, and if you so 1 into this, so n plus 1, right? Plus 1, then an, this is equal to a n minus 1. Am I okay? Yeah.
In the first term of the summation, there should be 2 into m plus n.
There was there was 2. Yeah. Thank you. So because in the original equation it started with 2x squared, right? 2x squared y double prime. So then this is going to be 2m plus 2n plus 1, right? So this is going to be this. Thank you. Now I am correct, I guess. Okay? Fine? Okay. So now, yeah, I think I can take care of this. See, some of the stuffs may be repeated. Please don't worry about it. Some new information, I guess, is always going to come up from whatever you have already learned in your previous years of studying mathematics, to be precise, and ordinary differential equations. Okay. So now, if I look at the very first equation here, now the significance of a naught not being equal to 0 comes out. Are you getting my point? right? See, at the very beginning, I told you that A not equal to 0. Okay, so that brings us to the fact that from here, what I can do, and okay, fine. Here I am going to get your m minus 1, 2m plus 1 equal to 0, isn't it? Because A not equal to 0. Of course, that is going to give me m equal to 1 and minus 1. Okay, and you know this relation, you must write that this relation is valid for all n greater than equal to 1, n being integer. Is it okay? Fine. Because this reference formula, it has come from the infinite series starting from n equal to 1. Okay, fine. So now this has given me a reference formula. So basically an equal to your 1 by n plus n minus 1 and 2m plus 2n plus 1 an, and of course this is for n greater than equal to 1. So now from the above equation, from the equation corresponding to a naught, so what happened? I have found out m equal to 1. So if m equal to 1, so then case 1, for m equal to 1, your an becomes 1 by n into what? 2n plus 3, right? an. Okay? So
this will be right hand
an
side.
plus 1. This is an minus 1. Sorry. This is an minus 1. Yeah. So then, therefore, a1, because I have to start with 1 now, because n starts from 1. So this is going to be equal to 1 by, this is 1 into 5, right? A naught. Okay. Then I'm just going to find out a couple of sums, not more. A2, so 2 into 7, A1. So this is equal to 1 by 45 is 70 A naught. So maybe, okay, fine. So this is good enough. This is good enough. Okay, this is good enough. And then when case 2, let me try to do it here, squeeze it here. Case 2, n equal to minus half, then an equal to minus half, minus 1, minus 3 by 2. So it is going to be 2n minus 3 by 2, 2n minus 3 by 2, and then this is minus half, this is going to be minus 1, and 1. This goes up, right? I'll be left with 2n. This 2n with this 2, it will go out. So it is going to be into n, n minus 1. Okay, fine. So I mean a1 is going to be, so this is minus, no, minus 3. This is 2 minus 3, right? So this is minus 1 and 1. So this is going to be minus a naught. Okay. A2 is 4 minus 3, so 1 into 2 a1. So this is minus half a naught. Okay, that is fine. I'll do more exercises later on. So I just want to emphasize on something that is right. So, like say, you have found out that I have been able to find out 2 independent series here. Okay, so basically what they do here, see in Frobenius series, eventually you will see that they take a not equal to 1. Why a not equal to 1? Because what is going to happen? Because in both the cases, then you are going to get something like, say, from here, you are going to get something like a naught into, like, say, let me tell you what you are going to get. 1 plus 1 by 5x squared. No, 1 by 5x plus 1 by 70x squared. And from this one, just a minute, x to the power 0. And then from the other one, x to the power minus half, again a naught, what I'm getting 1 minus x minus half x squared, and so on. Okay. Anyway, so now if you look at these two, then generally, I mean, whenever we consider some linearly independent solution, so what we do, y equal to c1 y1x plus c2 y2x, isn't it, right? But here you see that, I mean, both the constants, I mean, they're the same. So that is why it is a convention that whenever you consider, I mean, Frobenius series solution, so then you simply plug in a naught to be equal to 1, and then so that this series is going to be this and this series is going to be this, and simply what you do is x to the power 0 is simply 1, so simply plug in some constant here, c1 into this, c1 into x to the power minus half into this. Okay, is it okay with everybody? Fine.
Sir, M was 1, not 0.
Yes,
X.
sir.
Oh, I was 1. So C1 x. Thank you. C1 x. Okay, fine. So now you have seen that I have found out 2 linearly independent series solutions. Is it okay with everybody? Fine. Isn't it? I mean, although I haven't checked, but they are linearly independent. I mean, these 2 series solutions, they are linearly independent. I mean, one is not a scalar multiple of the other, definitely. Okay, so I have been able to find it out. But is it going to happen always? Right? What is the guarantee that you are always going to have 2 linearly independent solutions? Okay, and here you have seen that M1 and M2, they were not equal, right? So in that case, definitely I was getting 2 linearly independent solutions. Definitely, I mean, that is a very strong word here still. Okay, and again, what's happening if you look at the equation corresponding to A naught, the equation at the top here. So what was happening here? If I look back at my original differential equation, so then I don't even want this. Okay, fine. So if you recall my original differential equation, it was what? 2x squared, right? I think it was minus. Yeah. This was my original device equation, right? Oh, fine. So now let me try to put it in standard form. So if I try to put it in standard form, this is going to give me y double prime plus. So basically what I'm going to write it, I'm going to write it like this. Okay, so then this is going to give me what? Simply I'm going to get half, right? I'm simply going to get half here. Is it okay with everybody? Right? And then I am going to get just a minute. X square is already there, so simply divide it by half. Okay, fine. So now what you have to do, compare this with when I try to explain to you the rationale behind choosing Frobenius series as your solution of the given differential equation. So over there, what we did, we expressed this. This is nothing but say small px, and this is nothing but small qx as an infinite series. Okay, so now if I compare this as an infinite series p, this and so on, and if I compare this as an infinite series and so on. Now, if you look at this equation, this equation could have been written as your equal to 0. Fine. So now you can see that this half is simply P naught here, right? And this minus half, it is simply Q naught here. Is it okay? Fine. If I assume this coefficient, of course, x is here, the numerator to be px, to be an analytic function about x equal to 0, so that I can get an infinite series of this type. And similarly for this, I mean small qx as an infinite series in this shape, then your P naught and Q naught would have been given by half and minus half respectively. Okay? So what I want to say is that if P naught and Q naught is known, so probably, I'm still saying probably, the equation, the very first equation coming out of the coefficient A naught, it is going to be of this form. Okay, where P naught and Q naught are nothing but the constant terms in the infinite series considered, where x is in the denominator and where here x square is in the denominator. Is it okay? Are you finding it a bit confused? Yes. Is it okay?
Yes, sir.
Yes, sir.
Right? So I'm still not confidently saying that it has to be P naught and Q naught, but here I have seen that it really worked. Okay, fine. So again, the general way of finding out the solution by substituting the Frobenius series, I'll come to that in a little while from now. But before that, Let me give you one example. And then from there, it is going to create a bit of controversy. I mean, if I give you that example. Okay, just have a look at this question. I'm just going to tell you, I mean, what happens with that. Okay, so let me tell you that, I mean, if you I mean, if you substitute a series solution of this form, here, okay, here. So this is going to lead you to, an equation of this form. Of course, you know what this is called. This is called Indicial equation. This is called Indicial equation. Okay, and from where one root is going to come out as 0. Okay, so in that case you know that. I mean, this series solution is exactly like the way you did for, I mean, ordinary part. Is it okay? Fine. So then I mean, again, from the recurrence formula, you would find out that your corresponding to m equal to 0, you are going to get an infinite series of this form. Infinite series of this form. Okay? Is this series convergent? Is this series convergent? Hmm?
No.
No.
No, sir.
Can I have an yes, please?
Except at 0.
Huh? Yes.
There is 0 multiplied by
Yes.
0.
Okay.
It is convergent.
This series. I mean, yeah, this series exists only when x equal to 0. Right? Is it
No, we did not
okay?
follow this 0.
Haha.
I did not
Yes.
follow this 0. This you wrote something 0 in previous.
0. Oh, okay. Oh, here. Sorry.
This is
Sorry.
x
I
to the
think
power
0.
0.
Uh-huh.
This is x to the power
It
0.
was x to the power 0. Sorry. Anyway, it was x to the power 0. So now, anyway, this series is divergent. This series is divergent. I mean, except when x equal to 0, right? Okay. So now, when I plug in this series in the given differential equation, because I know that the only convergent series that is possible out of this is when x equal to 0, right? And that leaves me with simply y equal to 1, isn't it? If I plug in, I mean, here, say the series is going to be what? Isn't it? It is going to be something like this, isn't it? Fine. So once I plug in x equal to 0, so this is factorial 0 is simply 1, right? I am going to get y to be equal to 1. Is it okay with everybody? Fine.
Yes, sir.
Yes.
Yes, sir.
Now, if you plug in y equal to 1 as the solution here, does it satisfy the given differential equation?
No, sir.
No? Yes. Because here I am going to get y equal to 1, but this part is definitely going to give you 0, so I'm getting 1 equal to 0, right? Okay. So that means the Frobenius series is not always going to work, right? Okay. So it is going to work only under certain circumstances. Okay, fine. So we are going to find them probably in our tomorrow's class. Now, before that, let us see the general method. Let us see the general method of finding the solution of a differential equation having a regular singular point through the Frobenius approach. And after that, I just show you the theorem which guarantees a Frobenius series solution of the given differential equation. And then you will realize that in the done the proof of the theorem partially halfway through, and only the convergence part we'll have to prove later on. So that I'm going to give you some hint through which you can easily do that. Okay. So now let us go for seeking a general solution. Okay. Let us go for seeking a general solution. So yeah. So you already know that these approaches can sometimes fail. And whatever example I have taken, so that has given you two linearly independent series solutions. But again, that may not be always so. Why that may not be always so? You are going to have that answer now. Okay, fine.
Sir, how we
Yeah.
show that y equals to summation n factorial x to the power n, this not holding, this is not satisfying this Frobenius method concepts of this OD?
Yeah, there must be some reason, right? So
Yes.
basically, I mean, any series is not going to satisfy it, right? Whatever series you, take, that series must be under, we must put those kind of series under some prescribed conditions, okay? So I'm going to give you a theorem. So definitely you will see that this particular series that I have given, factorial and x to the power n, it doesn't satisfy those prescribed conditions, okay?
Sir, at first this series is not convergent, so this is the first mistake we have.
Okay. Series, but it converges for x equal to 0.
Yes, but it is not convergent in the neighborhood of 0.
No, I mean, it is not convergent in the neighborhood of, yeah, you are right, because basically the hint lies in your radius of convergence being 0.
Yes.
Okay, radius of convergence being 0. So the radius of convergence must be non-zero in order for a Frobenius series to be a solution of this. You will find it out.
Yes, sir. Yes.
Okay. You will always see that r greater than 0, we always assume that. Why so? Now you have got a probable answer, right? Okay.
Yes.
So, fine. Okay. So again, this is my differential equation, and of course I am assuming that x equal to 0 is a regular singular point. Okay, so x equal to 0 is a regular singular point. That means that x px is analytic about x equal to 0. So similarly, x square qx, this is also analytic about x equal to 0. So that means I have a series of this form, right? And similarly, I have a series of this form un x to the power n, and of course I can assume that, like say, let them be, convergent in this interval, and of course I am assuming that r is greater than 0. I am assuming that capital R is greater than 0. Okay, and then I am assuming that the Frobenius series solution is y equal to your this x to the power n equal to 0 to infinity, your an x to the power n, or maybe I can write it as, now that you are familiar with this, simply n plus. Okay, fine. So now what I'm going to do here, so firstly, like say your y double prime. So this is, I have already done, n equal to 0 to infinity. So your n plus n plus n minus 1 x to the power m plus n minus 2. Okay. So now, just the next two manipulations. Please be careful about what I'm going to do. So, see this. Right? I can write it like this. Okay. So then from here, this gives me your this n equal to 0 to infinity n x to the power n, and of course you know that this is n going from 0 to infinity. Your here I have missed an, so similarly an plus n x to the power n plus n minus 1. Okay, so now what happens? If I rope in this, just a minute. Just give me a little bit space. Okay, just let me write it down. n plus n plus n minus 1 x to n plus n minus 2. Okay, so this is written as x to the power n minus 2 n equal to 0 to infinity. Okay, fine. X to the power n. Okay, so similarly, what I'm going to do, this also I'm going to write it like this. I'm going to take xc. Now, this is 1 by x, so this is going to be x to the power m plus n minus 2, right? So that means x to the power m minus 2 I can take out, and then this is going to give me, I mean, n equal to 0 to infinity. So maybe I can write it as, like say, n plus n an. So this is one series, and then n equal to 0 to infinity pn x to the power n. Okay, so now just one more manipulation. See, this one, okay. So this is equal to x to the power n minus 2. Now, if I multiply these two series, you know what is going to happen. So this is n equal to 0 to infinity, right? And then obviously x to the power n, k goes from 0 to n. Can you tell me what it is going to be? Is it okay with everybody? Right?
Yes, sir.
Yes, we have already done multiplication of two series. So I am going to do one more manipulation, but before that, let me work out the other part. So basically, your this one, your qx y. So as before, what I'm going to do, I'm going to write it as 1 by x squared, your x squared qxy, right? And you know that your this can be written as an analytical series and going from 0 to infinity, and of course from this an and x to the power n plus n and going from 0 to infinity. And as before, because of the presence of this x squared term, what I can do, I can write it as this n equal to 0 to infinity an x to the power n, and then n going from 0 to infinity un x to the power n, and now I can easily write it as n equal to 0 to infinity x to the power n, and of course this is k going from 0 to n, and this is pretty straightforward, ak q n minus k, right? This is, I mean, pretty, isn't it? This is pretty obvious. Is it okay with everybody? Fine?
Yes, sir.
Yes. So, okay. So now, I'm going to do one more manipulation. I'm going to do one more manipulation. So, what is that? So just please look here carefully. Okay. So maybe I can, because this I already have the expression, right? Yeah. This also, I already have this. Okay. Now, what I'm going to do here, this is actually for n minus 2. Let it be like this, and equal to 0 to infinity. Now, see here, what I'm going to do. Firstly, I'm going to run my index k from 0 to n minus 1. Okay, n minus 1. So basically, this is going to remain the same. N plus k, ak, p, n minus k. Right? And then what I have to do, simply in place of k in my next term, I have to plug in n. Is it okay with everybody? Fine? K equal to 0 to n minus 1, right? And then the next term is going to be simply k corresponding to n. Is it okay? So that is going to leave me with n plus n, a n p p what?
P naught.
0.
P naught, yes. Fine. And similarly for this one, it is pretty straightforward. This one, it is pretty straightforward. It is x to the power n minus 2 and equal to 0 to infinity. And then k equal to 0 to n minus 1, ak q n minus k, and this is pretty straightforward, plus an q 0. That's it. You will get to understand why I have done this manipulation beforehand. Now, okay, fine. See, we have got all of them. We have got all the terms. So basically, then what is going to happen? So this was simply px y primes, right? So the given differential equation was y double prime plus this and plus this equal to 0, right? So once we plug in all the values here, and if I cancel out x to the power n minus 2, then what I am going to get? Now you get to know why I am doing all this stuff. Okay. So what I am going to get, maybe just concentrate here, concentrate here, and concentrate here. Okay, let me add them up. How much time do I have? Okay, I think I don't have enough time. Okay, fine. So maybe I will. Okay, these three terms. Huh? So because you have already understood, I can remove this x to the power n minus 2 also. Yeah, I have already done that from here. So this is number 1 term, this is number 2 term, and this is number 3 terms. Okay. So if I add them up, now you see what is going to happen. Yeah. So adding all of them and cancelling your x to the power n minus 2 term, I am going to get from here n equal to 0 to infinity. So now what I am going to do, firstly, I am going to rope in all the terms coming along with an. Okay. So from here, what I'm going to do, say I am having something like this. Okay. So for an, what I am getting from here, fine. Okay. From here, P naught. This is done. From here, this is simply what? Q naught, right? Just a minute. Yeah. Is it okay with everybody? Fine? Okay? And what I'm left to it now? What I'm left to it? I'm left to it now. K going from 0 to n minus 1, and simply this. M plus K, AK, P n minus K, and then plus AK, Q, n minus K. Is it okay with everybody?
Yes, sir.
Yes. So now you know the rationale behind why I had taken that terms corresponding to k equal to n separately. Is it okay? Fine. So that I don't have to do a lot of manipulations. So under one umbrella, everything is going to come. So now we can work out the formula pretty straightforward. Okay, fine. 1%. Yeah, I think I'm fine. So now you equate different powers of the coefficients of different powers of x to 0. Now see. Okay, fine. Okay. So now when n equal to 0, this second term is redundant. So when n equal to 0, what happens? Firstly, you are going to get a naught, then your m minus 1 plus m p naught plus Q naught. This is equal to 0. Right? You have got this. So then when n equal to 1, when n equal to 1, what you get from here? You get A1, then n plus 1 into n plus n plus 1. Sorry, this is not n because n is already 1. M plus 1 into m, then m plus 1 into P naught plus Q naught. Okay, so then once you plug in n equal to 1 here, so this is going to be k equal to 0 to 0. So basically, this is going to involve only one term. Okay, is it okay with everybody? So now this is going to have what? K equal to 0. So this is going to have m A0 just a minute. N equal to 1, so it is going to be N1 P1 K0. Okay, plus Q1, sorry, A1, then Q, is it A1? This is A0. Okay, see, this term, say, this term, let us come back to this term again. Let us come back to this term again. See, here what is happening, I was plugging in n equal to 1. Okay, so basically it becomes from k equal to 0 to 0. See, when n equal to 1, so this term, it becomes, say, m plus k, ak p1 minus k plus ak q1 minus k. Fine? And here, k can take value only 0. K can take only value 0 because eventually it is k equal to 0 to 0. So basically it is only one term. Is it okay? So now, once you plug in k equal to 0, once you plug in k equal to 0 here, then you will see that this is m, then a k equal to 0. So that means a0 p1 minus 0 this, and then a0 q1 minus 0 this. Is it clear now?
Yes, sir.
Yes, sir.
Yes, fine, fine. So this is the way it is. So now this is equal to 0. I'll do one more. Say when n equal to 2, what happens? Say a2, then m plus 2, m plus 1, m plus 2 p naught plus q naught. So now let us work it out. Let us work it out. So let me firstly write down k equal to 0 to n minus 1, right? So this is going to be 0 to 1. So let me write it down once. Say m plus k, a k p n equal to 2, 2 minus k plus a k q 2 minus k. Fine. So then what is going to happen? So this is going to give you when k equal to 0. So this is going to give you m your a0 p2 plus a0 q2, and then plus this is going to give you m plus 1 a1 p1 plus a1 q1. Is it okay? Fine. So basically this is going to give me this is equal to 0. But last I have to write one more expression. I have to write one more expression. So eventually, when simply n equal to n, say, n equal to n. So I am going to have a n. So m plus n, the same thing, m plus n minus 1. I'm not even bothered about this. N plus n p naught plus q naught. So now here the thing is going to happen. Can you see this part? Okay, fine. So here now when k equal to 0, so this is going to give me firstly m a0 pn plus your a0 qn. Okay, so then plus m plus 1 a1 pn minus 1 plus a1 q n minus 1. So in this way, once your k becomes n minus 1, you will see that this is going to become p1, isn't it? So the last term, it is going to become m plus n minus 1, then a n minus 1 p1 plus a n minus 1 q1. This is equal to 0, and of course there are more equations. Okay, is it okay with everybody? Fine. I'll come back to this again in my tomorrow's class. But please, whatever I have done, please, practice this at home, so that this kind of expression for you guys, it is very easy to work out. Okay. So now, then again, I am going to define a new function, and based on the function, I am going to interpret this series that is going to arise out of the roots of this equation. Okay, of course, now formally we can define indicial equation. Is it okay? I know that it is pretty lengthy and very mechanical, but again, each step is going to tell you something, tell you some story later on. Don't worry about this being mechanical. You will see that from this equation, the last equation, I'll be able to interpret many of the possibilities that is going to arise out of the roots of the indicial equation. Okay, fine. So then I will meet you tomorrow at 12.